All right, as mentioned, going to do a video on the use of the F-Tafel. So this would be a site reduction table, set of tables produced by the Kriegsmarine during the war. This particular edition is the third edition, was brought out in 1941. The Germans used various site reduction methods to reduce their celestial observations into lines of position. The common one was Fulst nautical tables, and then the F-Tafel was also common, and then also they came out later in the war, I should say about mid-war, with a sort of a cylindrical slide rule to help compute, to do the computations as well. But I like this set of tables the best. I think it goes pretty smoothly. There are modern methods too of site reduction, tabular site reduction, that are easy, but this kind of gives you the good feel of what they would have been using at the time. And so I printed these tables off. I know that Alpheratz has a link in his documentation, in his videos, to the PDF of this. So it can be used electronically, obviously, digitally. I like this printed out on paper because of all the sections, and while you're reducing a site, there's a lot of back and forth that needs to happen. And so I like it on paper, but you know, for personal preference, obviously, right? So so I've got these in a binder printed off, okay? And it's pretty worn, well worn, because it's gotten some use. So in SH5, I have started a new patrol. I'm heading northwest to the Fair Isle Gap to shoot the gap out into the Atlantic and head up toward Iceland. Those are my orders. And so I am kind of halfway up, not quite halfway up the North Sea at this point. So my DR position is 55 degrees, 58 minutes north, 4 degrees, 33 minutes east. It's the 23rd of November, 1939. I've taken a two-star site, a two-star observation at 2 stars in the evening for evening stars. This is Alpheratz and Altair. These are the altitudes that I measured with the in-game sextant here, and these are the times down to the GMT, the UT times that are provided in the sextant interface down to the second. Okay, very important. So that's the data we've got. For this, I'm going to use the, so Alpheratz has created, so Alpheratz is the, you know, he's taken his name from this star, obviously, but he's the individual that's kind of made celestial navigation sort of feasible in the game. He's gone through and fixed various sets of data with regard to the stars and the moon and the sun, to make the adjustments that you would apply in real life also apply to the game. He's also figured out the declinations of various bodies, stars, planets, or excuse me, not planets, stars and the sun, to make it so that you don't have to do any other adjustments. You just pull the numbers right out of his almanacs and you're good to go. What he's also done, which is incredibly impressive, is he's taken the format of the historical German nautical almanac and he's recreated it and put it together for SH5 using the in-game star data. So importantly, he's fixed the SHA, which is really this here, and he's fixed the declination, which is this, and tabulated all of these so that these values are actually correct and match up with the game. If you use a nautical almanac from these years that's historical, you won't get to the same answers because the declination and the SHA of various bodies in the game aren't correct, or at least historically accurate. So anyway, so he's done this. I've printed the pages out. If you're familiar with how a nautical almanac looks nowadays, this probably looks like wizardry. The German nautical almanacs not nowadays, but they certainly were back then, were more like astronomical almanacs in the sense that they use concepts like the true sun, the mean sun, you know, concepts in here. They've laid out the equation of time for each, you know, for each in 2 hour intervals by day. It's different, but I think it's more fluid when you're going through these and you're doing the math. You're adding the hours. You're really working in hours instead of angles, right? It's your hour angle. So you think of like LHA. It's your hour angle, but it's expressed in a time figure. Okay, so it's a little different, but we'll walk through how this calculation works. And Alpheratz also has, I think he has a video called "What is Real Navigation in SH5." He goes through the same thing using his almanacs that he's put together. He's gone through an F-Tafel demonstration as well. It's not narrated, but I will narrate mine. But his is much more well done than this will be. He's got, you know, he's got subtitles and text on the screen. This is just going to be me talking, as are all my videos, because I'm terrible at editing. So anyway, so that's the data. So we've got the right page for the 23rd of November. Okay, so the first step we're going to do, we've got the altitudes, we've got the times, and we've got the names of the bodies that we've taken. So we'll start with the Alpheratz first. So the first thing we do is we always start with the time, and we say, okay, it was 16:21:15 is when we took the site. Okay, that is UT. And then the next thing I need to do is I need to adjust for my longitude. I need to get that into a time figure. So if you remember with sight reduction, if you're familiar with how sight reduction works, you know, if you're working in angles, you take your GHA, you know, and figure it out down to the second, and then you would add an east longitude or subtract a west longitude. It's the same thing here. We're just doing it in terms of time. So we say, okay, 4 degrees, 33 minutes. I open up the F-Tafel and I go to the appropriate section, and I get these tables here. Verwandlung von Zeitmaß in Gradmaß. Okay, this is conversion of a measurement in time to a measurement in angles. I don't want that one. I want the other one. I want to go from an angular measurement, an angular quantity to a time quantity. Okay, so my longitude, 4 degrees 33 minutes. I find 4 degrees, that corresponds to 0 hours and 16 minutes, and then 33 is, now I'm looking at minutes, that's 2 minutes and 12. So if I add those together, I get 0 hours 18 minutes and 12 seconds. So 18:12. Okay, 18:12. So I add that since I'm east, plus 18:12, and that's for longitude. Okay, so that gives me 27, 39, 16. Okay, so far so good. The next thing I need to do is I need to pull up the almanac for the particular day in question, 23rd. And I look here, and this is mittlere Sonne, gerade Aufsteigung. Gerade Aufsteigung is the right ascension of Aries. Okay, it is the hourly angle, the hour angle, working from west to east around Greenwich to Aries, to the point of Aries. Okay, so that is, well, I should say from the sun, from the mean position of the sun all the way around to the right to the point of Aries. Okay, so doesn't matter. All we need to know is that we need to add that figure. So some interpolation is required. The number we're at, so we look for our UT figure, which is 16:21:15. We find the 16 row, which is here, 16 hours, 6 minutes, and 54. But since we're 21 minutes into the hour, that's like call it 0.4-ish, 0.4 hours. These change by 10 seconds per hour. You can see that we go from 34 at 2 p.m. to 54 at 4 p.m. Okay, we use that to our advantage and say, okay, every 10 seconds is an hour, so whatever decimal of an hour we're at, so in this case we're 0.4 hours, we just add 4 seconds. So we say, okay, we're at 6:54. I want to be at 6:58. So I add 6:58. Okay, and this is what's known as the right ascension of Aries. Okay. All right, so then I do the math. I say, okay, this is 15, 5, 6, 7, 8 is 2. You'll get good at adding, minutes with practice. Okay, we carry the 1, so that's going to be 16. That's 46. And this is 32. Well, oh boy, we're over 24. Well, we'll fix that in a bit here. Okay, so that's good there. So 32, 46, 25. So far, so good. The next thing we need to do is the right ascension of the star itself, which is, we'll just label it star, okay? And then that we get from another table in the almanac, Fixsterne. Fixsterne, these are going to be the fixed stars, okay? These say fixed because they hardly move. They're so far away. They're an infinite distance away. They hardly move, right? So for purposes of SH5, they don't move. This entire almanac just has these 2 pages for the stars. That's it, okay? Gerade Aussteigung, again, that's the right ascension. That's the number we need to subtract now. So we find that for our star, we're looking at Alpheratz. We need to subtract 0 hours, 5 minutes, and 26 seconds. So we say minus 0, 5, 26. We should get that centered. And then that leaves us with 59 seconds there. And that's going to be 40. And then that's 32. Okay. All right, so far so good. 59, 0. Okay, yep, that's good. So what do we do now? We're over 24, so we got to subtract 24 from this. We'll just do that in our head. That leaves us with 8, 40, 59. Okay? 8, 40, 59. What that means is if you think about if you think about the Earth, and Alpheratz has a good drawing of this actually in his videos, but basically, if you think about it this way, what we're trying to get at is if you're here, right, and you've got, if you're here and you've got, and you're right, we're talking about right ascension here. So you're here on the Earth. This is right ascension, and if you go 8 hours, you're basically here. If you're looking at the Earth top down, you're basically 8 hours is here. This is 8:40. Okay. This is the other side of the Earth from where you are. So 8:40. What we're trying to arrive at is actually this particular hour angle here. So what we do, if this hour that we figure out is less than 12, we subtract, we get the other piece of it. So in this case, 0, 1, 19, 3. Do you see that? We basically took 12 minus this because this amount here that we figured out was less than 12. We needed to take 12 minus that to get the actual hour angle that we need, which is this. So this is our hour angle here, okay? And we call this T, O with an Umlaut. That's Stundenwinkel östlich, okay? It's an easterly one because this is less than 12. Okay, I should write that the other way, right? So this is, so this is less than 12. We need to subtract it out of 12 to get the answer. If it's the other way around, if this amount is bigger than 12, we just subtract 12 from it, and we call this TW, westlich. Okay. All right. So the important thing to know about the F-Tafel is it works in minute increments of 4. So what we need to do with this number is we need to say, okay, what's the closest? We look at 19. What's the closest number that's divisible by 4? Well, that's 20. So we say 3, 20, 0, 0. That's the hour angle we're going to use for the table lookups. But we have to note that what we chose was bigger than the amount that we calculated by a certain amount. And that amount is, we say plus, because we're going with a larger minute figure, plus 0.59, right? Because we chose an hour. We ended up choosing an hour, or excuse me, a minute that was 59 seconds greater than what we calculated. Okay, so we note that down. Because the hour angle is east, we note east. And then over here, we'll note either north or south, but we don't know that yet. We don't know that yet. If this 3 figure, this 3:19:01, were greater than 6 hours, we know it's north, or we know it's the same as our latitude, in this case north. But it's not, right? Because it's 3. But if it were 6:19 or 7:19 or 8:19 or whatever, we know it was north, so we would write north down, but that's not the case, okay? All right, so we have our time figured out. The next step is to get the declination, and then we write U, and then we write, this is my own little notation. The F-Tafel form, there's a site reduction form that's included in the tables. I'm not using it. I'm using the kind of the compressed version that I like to use. Okay, and I write V here, because these are what we need to look up. So the declination, German, that's called Abweichung. Abweichung for Alpheratz is north 28, 48.8. So I write that down. 28 degrees, 48.8 minutes north. Okay? Now I need to name this. North or south. There's actually rules that you'll get to sort of memorize over time, but in the first part of this, these tables, there's rules at the bottom. They're in German, of course, but what it's basically getting at is for ungleichnamig Breite, wenn t weniger als 6 Stunden ist. Okay, so basically, if U is the same name as, or label, if you will, as your latitude, if T is less than 6 hours. Well, we know T is less than 6 hours. It's 3:19, right? So we know that U is the same name as our latitude. So we note that down. North. Okay, that's good. And then I draw a line here because I'm going to do addition here, and then we're all set up now. Okay. So the next step is I have to find my rounded to the nearest divisible amount by 4 T value in the tables, in the first part of the tables, which is section table F1. So I'm looking for 320. So you can see they increase by 4 minute increments up here. I just find the page that says 320. There it is, right here. This is the column that I'm looking for right here. Okay, so with that information, the first thing we need to do is we need to find a value called P. Okay, and P is going to be a help, like a helper number for us to figure out what the azimuth is later. So for P, what I do is since I'm in the 320 column, I use my declination, which is 28.8. 48 is 0.8, 28.8. All right, and I find that in this here, 28.8. Okay, well, here I've got 40. This is column P. 28.8. that difference there is 0.5. All right, 0.5. So if I say, you know, 0.5 times 0.8, I need to add 0.4, just mental math. 47.8 is my p-value. So I write that down, 47.8. I'll need that later. Now, staying in the same column, I go and I find the nearest latitude line to my DR position, whole latitude. I think I'm at 55, 58 north. Well, that's only 2 minutes, arc minutes away from 56. We use 56. It'd be the same thing if it were 55, 31. Since we're closer to 56, we use 56, okay? So this is what we're going to use for our assumed latitude. The longitude we're assuming for plotting purposes is the same. We always plot on our meridian with this method. But we plot to the nearest whole latitude line, okay? Okay, so 56, so in the 320 column, we go down to find row 56 degrees, which is here, and we're pulling numbers. We're pulling 23, we pull in U, this is the U column, 23 degrees, 26.4, 23 degrees, 26.4, and we're pulling V, which is 995. It's a logarithm, 598. And we're also pulling another helper value called GRD. That stands for Grenzday. So it's a way for you to know whether or not it's actually an angle in the spherical triangle, at least the way the spherical triangle is constructed for purposes of this. It's a way for you to figure out what the azimuth is, whether it's going to be north or south. So GRD is 43.6. We compare that with our declination. The declination is the latitude of the body. You know, it's what latitude the body is on. If you were to shoot a ray right down from the celestial body to the Earth, it's the point on the Earth, the latitude that ray beam would hit. Okay, so 43.6, 28.48. The declination of the body is less than GRD. It's south. Okay, that's how we figure that out. All right, so we're good there. So now we add D plus U. We add them if the name is the same. We subtract them if the name is different. The name is the same, so we add them. All right, and again, there's rules down here for the azimuth rules. So if I mentioned this before, if T is greater than 6 hours, the azimuth is from the upper pole. That means north, if you're in the northern latitudes. If you're south, that means if you're in southern latitudes, that means south. Upper pole, okay? If T is less than 6, which in our case is the case, declination and latitude if declination and latitude are the same name, and declination is greater than GRD, then it's north, okay, or upper pole. If declination and latitude are the same name and D is less than GRD, which was the case for us, 43.6 versus 28, okay, then it's from the lower pole, in this case south for us. But if declination and latitude are different names, like if the declination were south and you're north, you know it's lower pole, it would be south, okay? So that's the rules there. All right, so we do the addition. We say that's 0.2, that's 5, 4, 5, 6, 7 is 1. And then we carry the 1, which is 12, 52, 15.2, okay? Now we go to F2. We go to table F2, next section, and we find that angle, 52, 15.2. $52, 15.2. That's the rows we need right there. Might be hard to see, but it is 89,801 is 15, and 16 is 89,810. So we do a little mental math. We need to do interpolation. Luckily, the creators of this made F-Tafel, which means basically interpolation tables, in order to help you out. So we're looking for a value of 15.2. So we do the mental math and we say, okay, what's the difference between the 15 and 16 values? It's 9. We can just see that, right? 810 minus 801. So we go to the 9 here, and we're looking for 0.2. So that's 1.8, just rounded to 2. We need to add 2 to the 89,801 figure. 989,803 is what we need. We write it down here. 989,803. Okay? We add these together. When you're adding logarithms, you can see this. I got 18 here. 9 plus 8 is 18. Carrying the 1 gives me 19. Just write 9. You drop the 1. We're still at 9.85401. Okay? Now we find that number in this table, and we look up. And that's going to give us our altitude. So 9.85401. We're looking 9.85. Right here, 85401 is between 4536 and 4537. Okay, so we write 4536. And now we do the interpolation again. So we need 9.85401. That's somewhere between 85399 and 411. Doing the mental math, I know that's the difference between those is 12, and my number is 401 minus 399 is 2. So 2 and 12, it's 0.2, okay? And the closest is 0.2. Let's just double check that. 36, 985, 401. 2, 12. Oh, I was pointing up here before. I'm sorry, 12 is here. So again, 2 is 0.2, okay? So that's 36.2, okay? So we've got an unadjusted altitude here that we've computed. We need to now take this number and go back to F1. And we need to do a couple things. We use our p-value of 47.8 and our initial computed height of 4536, and we cross-reference. So we're going through and we're finding 47.8, 4536. P-value of 47.8 and 4536. Okay, you can see we're in the 60s, and we need to find a p-value of 47.8. Okay, so we look. We scan. 47.8. Okay. 45, 36.2, 47.8, 45, 36.2 here. 47.8 would be about here. Okay, so it would be an azimuth of about 74. However, this dotted line here, when you're doing this exercise, if the answer falls beneath this dotted line, there's a separate section that you need to do here to actually compute it more accurately. I'm not going to demonstrate that just in the interest of keeping the video moving. Just know that when you're doing this and you run into that situation, you need to actually go and figure it out more accurately using these other tables back here. Okay, I'm not gonna go through that now. I've already computed these sites, and I know the azimuth is going to be 73, not 74. This is where you run into problems, because you can see for a computed height of 4536, these two numbers don't differ. Azimuth of 73 and 74. You can see 48.4, 48.1, 49.3, 49.0. what do I choose? Like my p-value of 47.8 could like be in between either one of these. So what do I choose? That's why, it's because these p-values don't change much per azimuth degree. You need a more accurate way to figure it out. It's in the other tables back here. Okay, so I won't go through that exercise, but there are instructions in there on how to do it. Okay, I know my azimuth is 73, so let's just pretend it was like clear from this that it's 73. All right, so I write 73. That is my azimuth. I'll draw, when I draw this out on the next part of this video, there'll be part 2 on YouTube. It'll be the actual plotting of this. You'll see I'll draw an angle. This is like straight south using the protractor, like 73. So this right here, that's how you draw it on the map. But I'll show you that when we get that far. Okay, so we have an azimuth. That's what we need from that step. Now we go to section F3. This is what I mean about having to flip back and forth. All right, section F3. I have my makeshift paper straight edge here. So now this is a triple entry table, basically, that allows you to pull out the adjustment that you need because the tables are set up in increments of 4 minutes. Okay, and we had to round up to that, so we had a spillover of 59 seconds that we need to account for somehow, because our real time was 319. Our angle is 319, not 320. We had to use 320 because that's how the tables are compiled. All right, but since we didn't, we have to account for that 59 seconds somehow, and it's using these tables. Zeithöhenverbesserung. Okay, that's your altitude correction for time. Okay, so what I do is I say, okay, what's my azimuth? 73. What's my assumed latitude? 56. I find 56. Oops. I find the 56 column here, and I read down, and you can see 73 lies between 71 and 77. So we'll go with that. Normally they're closer together, but when the azimuths are large like that, they're not. And I have to say, okay, I have to find 59 seconds. So between these two columns, I have to interpolate. Because it's 73 and not 71 or 77, I can just eyeball it in my head. I'll pull 6.6. 73 is closer to 71 than 77, so I'll use the 6.6. And then I'll use, because this change is 3, I'll bump it up 1 and say, so I said 6.6, and I'll say 8. So between 6.6 and 8, all right? Or no, keep 7.9. Just keep it easy. 6.6 and 7.9. That difference is 1.3. You can just do mental math for that. Well, I need to interpolate for 9 in between because the number I need is 59. So, and we're working on 50 and 60 values. So 1.3, if you just do mental math times 0.9, you can do that in your head. That is like 12. So in these terms, it would be 1.2. Okay, 1.2. So I would say 6 plus 6 plus 1.2 is 7.8. 7.8. That's just mental interpolation. Okay, 7.8. Because this is plus, because we were too high, we add 7.8 to this to correct it, which gives us 45 degrees, 44 minutes. That's the computed altitude. So we have a computed altitude now, and we have an azimuth. Those are the two things we need for a site. Okay, but we're not done yet because we need to adjust our observed altitude with the Gesamtbeschickung. So 45 degrees, 47.6 was our observed height. Okay, we go to the tables which are in here. All right. Mondrandis, we don't need that. Fixstern, okay, Fixstern and Planeten, we need Fixsterne. So Fixstern, so we know it's 5, our height of eye is 5 meters, always, in the game. So, Gesamtbeschickung für den Kimmabstand eines Fixsternes oder Planeten. We don't care about planets, we care about stars, okay? So this is the cumulative adjustment for the altitude of a fixed star, okay, or planet. So we know the height we measured was 45, 47.6, so we find the closest in here on the 5 column, 45, so the adjustment is going to be 5, and that's a minus, you can see here. So minus 5 is going to give us 42.6, so 45 degrees, 42.6. Now we have to compare our computed with our observed altitudes, 45, 44.0. And since our computed altitude is higher than the observed altitude, that means we are further away from the body than we thought we were. And we are further away by 1.4 nautical miles, okay? 1.4. You see that? And we say away by just doing a minus sign there. Okay. Okay. So these are the important pieces of information right here. 1.4 away and at 73 south, 73 east. That's Alpheratz, okay? I'm 37 minutes into the video and we've done 1 star. Oh my God. It takes significantly less time with practice to do this. Me explaining it is obviously going to take a lot of time. Okay. So that's a site. That's Alpheratz. We will do Altair now. I will do it, I guess for demonstration purposes. Maybe I won't talk with this one and I'll show you how quickly it can go. If you aren't worried about trying to explain it. Okay. So I'll try to keep this somewhat centered on in the video here, but at any rate, here we go. All right. So again, I'm pulling this site here, 4124.4 and 16. This is the this is UT 1622.48. Okay. So here we go. I'm using the same longitude because we're assuming we did these in the same position. I hardly moved at all between the 2 sites. Okay. The other thing to note about this is because this time is practically the same, we use the same right ascension. Okay, 1606.58. Altair now, which we get the there. 1948.1 is what we need to subtract. Bigger than 12, we know it's west, we subtract 12. Closest 1 to 4 is 1, 0, 0, 0, 0. And that leaves us 2 great by 3 seconds. We know it's west. We don't know whether it's north or south. Okay. D, U, V. 844.5 north. We know this is also north. Okay. Eight 44.5. Oops. 75.2 is P. All right, and then we're at 56 degrees north. So we say 33.5.1. And then V is 9.99. 540. Do this 6. 49.6, and that is 41 degrees, 49.6. Okay. 49.6, 41, 49.6, 41, 49.6. All right, 49.6. That difference there is 14, and I'm looking for 0.6, so I have to add 8. So I go 82,404, 9.82404. Okay, 9,81944. So we know it's 41. 81944, 4117. That's at out of 15. 15 is 0.3. 17.3. Okay, and then I find my azimuth, 4117. So I'm looking for an altitude of 4117, and then I'm trying to find 75.2, the p-value here. 41, 75, 75.2. So 4117, between 41 and 42, 75.2. The azimuth is going to be 20 degrees. Oh, the other thing I forgot to do is get GRD. So we need to go get that to figure out whether it's north or south. So again, I look at the 1 hour, 56. GRD is 55.1. Our declination is 8, so it's clearly south. Okay. All right. Okay, now we need to interpolate for to correct for the number of seconds. So we go F3. And we say azimuth is 20. Latitude is 56. So look at that. We've got a 20 number under 56, and we're concerned about 3 seconds. Okay, so 56, 20. We look between the 0 and the 10. 3 is like 0.2. Okay, interpolate between the two. So we have, since this is plus, we have to add 2. 0.2. Okay, so 41, 17.5. Altitude was 41, 24.4, which we correct. .1. .41, 19.3, and then we compare 41, 17.5. Since observed is higher than computed, we know this is plus. We're closer to the body than we thought we were. All right, so the next video will plot these. So that's the side. So you can see it's takes a lot, and it would have even been quicker. I was still adding commentary to it for the second site, but you can see it's pretty quick, and it doesn't take up a whole lot of real estate on a piece of paper. In fact, it takes even less than this when I do it in my notebook, which you can see. I've got these, I condensed these down pretty, there's these two sites right here. There's those sites on a small little corner of a piece of notebook paper. So, you know, it doesn't take up a whole lot of real estate, and you know, but I laid it out to try to demonstrate it. Okay. All right, so those are the two sites. We'll plot these in the next video. We'll go ahead and plot these, but for now, we have all the data we need to plot them. Okay, all right.